By default, overflow will cause compile errors, but we can add a global annotation to suppress these errors. So, as you can see, the largest possible number U8 can represent would be 255, meaning this would cause an error. Because again, 1000 is larger than the largest possible number a U8 can represent, meaning we have here an overflow error. Now we can actually allow overflowing by using this attribute. So this then won't complain, right? And then when we print out v, as you can see, we would get back 232, because we have seen over here that this would be the result when the compiler performs this operation. So we allow here overflowing literals, right? If we comment this out, then the compiler will complain, because this is actually not possible. When casting any value to an unsigned type t, tmax plus 1 is added or subtracted until the value fits into the new type. That's what we have seen. So in this case, 1000 as U16 would return 1000, right? Because a U16 can represent a number of 1000. But over here we would have an overflow, meaning this would return 232, like we have seen over here. For positive numbers, this is the same as the modulus. So this would actually be the same as doing 1000 modulus 256. Remember, U8 max plus 1, meaning 256. Now, we have also seen in the example when we have -1 and casting that to an unsigned integer, it will then basically just rotate. So this will return 255. Since Rust 1.45, the as keyword performs a saturating cast. When casting from float to int, if the floating point value exceeds the upper bound or is less than the lower bound, the returned value will be equal to the bound crossed. So in this case, we have a float here, casting it to U8, meaning a saturating cast will be performed. So it will just return the largest possible number U8 can represent, which would be 255. Now, in case we have here a -100 as floating point and convert it to U8, this just would return 0, the smallest possible number U8 can represent. This behavior incurs a small runtime cost and can be avoided with unsafe methods. However, the results might be overflow and return unsound values. Use these methods wisely. We can use here in an unsafe block the method toInt unchecked. So the compiler here won't actually check what's going on. So as you can see, we are casting 300 floating point to an uint to a U8. So as you can see, we are here casting 300.0 floating point to an U8 integer, and this won't be checked by the compiler. That's because it's in an unsafe block. Now this would return 44, right? Because 300 minus U8 max plus 1 would be 300 minus 256, meaning we would be left with 44. And minus 100 as U8, as you can see, we are typecasting this floating point to an U8 integer, and again this is unchecked. So again, what the compiler will do here, it will take U8 max plus 1, meaning 256, and it subtracts 100, meaning we would get 156. And not a number would be converted to 0, okay? And of course, here we have to use again the attribute allow overflowing literals, just so this will actually compile, because usually this won't compile. And as you can see, this would be the output. Now over here we are dealing with raw pointers, and we won't cover that in this beginner's course because this is more of an advanced topic. So see you in the next topic. So we have seen type conversions for integers and types from the standard library, but what if we want to convert types that we defined, basically custom types? And Rust has for this the from and the into trait. So let's see, from and into traits are used for type conversions between different types without requiring explicit casts. It's part of the standard library and can be implemented for custom types. Implementing the from trait for a type will give us the into implementation for the given type for free. Meaning when we implement from, we implement it into automatically. So always implement the from trait and not the into trait. Let's see here an example. We have a custom type number. And then over here we are implementing the from trait, right? So we want to convert from an I32 to our custom type number, right? And the from trait implements a method from. So we take here as an argument an I32, and we will then create a new instance of the number type with the provided value and then return it. And that means when we use here the from associated function on our custom type number and provide it an I32, then this can directly be converted to our custom type, right? And we can do it in two ways, from, as we've seen, because we've implemented it. And I've told you that when you implement the from trait, the into trait is automatically implemented, meaning we can also call the into method on the type we want to convert to. But when you use into, a type annotation is needed, so the compiler knows into what type you want to convert this type, right? So we convert here a type of I32 into a number, and this would be the implementation. So the from trait allows for a type to define how to create itself from another type, hence providing a very simple mechanism for converting between several types. The from and into traits are inherently linked, and this is actually part of its implementation. It means if we write something like this, So we implement here. So we implement here the from trait for the custom type u. Then we can use u from t, right? We can then create a u type from the type t. We have implemented the from trait on. Or we could also use into. So we convert t into u. The into trait is simply the reciprocal of the from trait. That is, if you have implemented the from trait for your type, then the into trait will be automatically implemented for the same type. Using the into trait will typically require the type annotations, as the compiler is unable to determine this most of the time. So for example, we can easily convert a string slice into a string. As you can see, we have over here a string slice, and then we can call string and the from associated function, providing it this string literal, meaning this will then be converted to a string. And we could also use the toString method. Again, this and this is exactly the same. And we could also then use the into, because remember, when we implement from, we get into for free. So we convert this my string literal into a string. And again, type annotations are needed. Because the standard library has already implemented this for us, impl from string slice for string. So we can easily convert a string to a string slice and vice versa. Some implementations of from can be found here. So as you can see, we have here impl from bool for i32, meaning we can convert a boolean into an i32. So when we have here a boolean value and call into, it will convert this boolean value into an i32 integer. In this case, this would be 0. 0 for false and 1 for true. And again, when we can use the into method, we can use the from associated function. So we call the associated function on the type i32 and provide it here the boolean value, right? So this will then actually be exactly the same. Fix the error in two ways. First, implement from char for. Maybe you should check the docs mentioned above to find the answer. Second, a keyword from the last chapter. So let's see the docs. So we want here to convert a character. So let's see over here. As you can see all the types that implement the from trait. So we want to go from character, and as you can see, we can convert a character to either U32, U64 or U128, as well as string. So I32 is not supported. And as you notice, these are only unsigned types because it's logical. A character can't be negative, right? It can't hold a negative number. So we only have unsigned integers here. So we can then in fact convert a char into a U32, let's say. So in this case, char implements. So in this case, we use here U32, right? We can convert from a char to a U32. Meaning when we change this over here, this should actually work. So we provide here a character called the into method, and then we should have an U32. Fix the error in 2 ways. So we can't use the as keyword here. This is not implemented, but what we can do is, let's first use the from method. So we can create a string, or basically converting a character into a string, because we have seen in the documentation this is actually implemented. And the second way would be to call a and then into, right? Like we did over here. Implement from for custom types. From is now included in standard prelude, so there is no need to introduce it into the current scope. So we don't have to import the from trait. It's actually in the prelude, meaning we can use it without importing anything. So over here we have a custom type number with 1 field. Now we want to implement the from trait for our custom number, meaning we should be able to convert from an I32 into a number. So when we call over here number from, right, then we should get over here number. This would then create an instance of the number struct, and the value field here will hold a value of 30, right? So, and the same thing is when we would call 30 like that and call into, right? This should then convert the I32 integer into the number type automatically. And remember, we only have to implement the from trait, because then we can use from and into both of them. So let's see. So this over here is the from trait, and let's take this function signature over here and copy it like that. Now in this case, self refers to number, right? And what we want to do is create here a new instance, and we just take the value, in this case the I32, right? And we provide it as a value for the value field. And again, because the name of this argument matches the name of the field, we can use it like that, and this is sufficient. So let's see. And this is compiling. So as you can see, then it's really easy to convert one type to a custom type we have created. When performing error handling, it is often useful to implement from trait for our own error type. Then we can use question mark to automatically convert the underlying error type to our own type. Now, we didn't cover that. This will be the next topic, but let's see the exercise. We have here an enum CLI error. Now, the two variants here, IO error and parse error, hold error types from the standard library, okay? And these are actually the error types that get returned in case of an error when using these specific methods that are implemented in the standard library. So as you can see, we want here to implement the from trait for different error kinds from the standard library, and we want to convert that to our custom error type, CLI error. So let's see, over here we have the function open and parse file. It takes a file name as argument and it returns a result, and we will cover results. So a result basically says in case of success it will return a result with I32 and otherwise CLI error. So then we call the read to string function, and as you can see this is defined in the fs module. Fs is used for file manipulation, and we provide to this function over here the file name. Now we pass a reference because this is defined in the documentation of this function. We are here using the question mark operator, meaning in case of success, the result type that will get returned will be unwrapped and contents will hold a string. In case of an error, it will return the CLI error, meaning the rest of this code won't get executed and we just get a CLI error instead. Now, the error type returned from this function would be IO error. So in order this error to be converted to a CLI error, we have to implement for this error type the from trait, right? But let's see what's happening here. We then take the contents, meaning this string over here that gets returned in case this function call is successful. And we then hold over here the contents of the provided file. Then we trim and then we parse. Now parse could potentially fail. And parsing is basically converting a string to an integer value, right? So in case of success, we will get out an I32. In case of error, we will get back a num parse int error. This is defined in the num module. Again, we'll cover error handling and all of that. Don't worry. This is now just about the type conversion. And then we return an OK with the num value here. We have to wrap it in OK because we return a result type. Now let's see how we would implement that. So again, I will just go to the documentation and copy the function signature like that. So we have the function signature, and then we can over here see what we want to do. So in case we get an IO error, we want to convert that to our custom CLI error. Now how would we do that? Let's change here the argument to E for error, and the type would be IO error, right? We are implementing it from this type. Now what we want to do is we just want basically to pass the IO error into the IO error variant in our custom type. So we can access the variant. So we can create an instance. Remember, this is the syntax to access the enum. So we access CLI error and then the IO error variant. And all we do then is just passing this IO error type, meaning we then have an instance of this variant holding our IO error. And that means we have then implemented the from trait for our custom type. So any IO error type can be implicitly converted to CLI error, meaning in case this function over here returns an IO error, it will implicitly be converted to a CLI error. Let's do the same thing over here for parse int error. this would be the arrow type from the parse method. So again, let's change here the argument name, and the type would be over here. And then we again just access this enum. We want to access the parse int arrow variant, and we pass it the actual error that gets returned. And this would mean we then create another instance of the parse error variant. Let's see if this works. And as you can see, this is compiling, meaning in case of an error over here, both these arrow types from the standard library, IO error and parse int error, will be implicitly converted to CLI error, right? Try from, try into, similar to from and into, try from and try into are generic traits for converting between types. Unlike from into, try from and try into are used for fallible conversions and return a result instead of a plain value. Now again, we use the result type, we will cover that, when there is a possibility of an error, of something going wrong. So as you can see, we have here an I16 holding 256. Into trait has a method into, hence try into has a method try into, right? This is the method defined on the try into trait. So we take this value here and call the try into method on it, meaning this will return a result. So we match this result. In case of an OK, then we unwrap the value from the result. And if it is an error, then we just print out the error over here and return 0, right? So in case this succeeds, then n will hold a U8 and the value. In case this fails, n will hold a value of 0. Now we have seen that when we want to convert an U8, then this would actually fail because this is out of boundaries. But because we are here basically error handling, that means that the program here won't actually panic. So in case this fails here, which it does, then we will just assign to n the value 0 and print out the error. So in this case, n would be 0. And again, error handling will be our next topic. So don't worry if this seems a little bit strange. Then over here we have a tuple struct even num, and it takes an I32 type. We implement here the try from trait for the custom even num type. Now here we have an associated type, and we define that it should be of type unit type, okay? And then we implement here the try from function. So all this function basically does, it takes a value and it checks if it is divisible by 0, and then we will return the result, in this case okay, even num, and inside it the value provided. Otherwise, if it is not divisible by 2, then we return an error holding our unit type we have defined here. As you can see, the type in case of an error would be this associated type error, meaning a unit type. So we have provided that over here. So then we can use the try from function. So when we call even num and try from 8, then this would return okay, right? Because 8 is divisible by 2. So we would get back a result, in this case okay, even num, and the value we have passed, right? That's what we defined here. Now, in case we try from a value of 5, this would return an error with a unit type inside, because again 5 is not divisible by 2. Now with try from and try into, it's exactly the same like with from and into. When we implement try from, then try into is automatically implemented. So we can use this try into method here directly. So we try here to convert 8 into this result, right? And the result in case of success will hold a type of even num and otherwise a unit type, like defined over here. And in this case, result will then hold okay, even num, and the value we have passed, 8. Now when we call try into on 5, then this will actually return error and a unit type inside, like we have defined over here. Let's see. And this is compiling. See you in the next topic. Let's now see 2 more exercises, and this time we are converting a custom type into a string. So to convert any type to string, you can simply use the toString trait for that type. Rather than doing that directly, you should implement the FMT display trait, which will automatically provide toString and also allows you to print the type with print line. So again, same thing like with from and into. If you implement from, then into is for free. So you usually don't implement this trait directly for a type. You implement display and you will get toString implementation for free. So let's see. We import here FMT and we have here our custom type point. Now here we are instantiating a point. So what we want to achieve here is that when we take the point instance here we have instantiated and converted to a string, this should then be the output. And we can also use the format macro here. Basically just providing origin, because the format macro will automatically convert that to a string in order to print it out, and the output will be the same. So let's implement the display trait here. So as you can see, this is the display trait and it provides one method. Now let's take it from over here. They provide here an example. And we can just copy this over here. Now I remove the lifetime, it's not needed. And let's implement the FMT method here. So as you can see, the FMT method provides here a formatter, meaning we want to write, we can use the write macro here, and the write macro works like println or format, but the difference is it will write to a buffer, in this case F. This is the formatter from the FMT module. And then we here provide what we want to print out. So in this case we want to print out the point is and the values. So let's do that. And then, like in a println macro, we provided the values. So in this case we want self.x and self.y. We want to print out the X and the Y field. And that's basically it. We have implemented the display trait for point, meaning our customly created type point can be converted directly to a string. So let's see. And this is compiling. So if we pass origin here, let's see the output. As you can see, this would be the output. So we can even manipulate how the output should look like. So instead of just printing out the two fields, we have even provided the output with a whole sentence, right? This will be the last one we will be doing. We can use parse method to convert a string into an i32 number. This is because from string is implemented for i32 type in standard library. To use from string method, you need to introduce this trait into the current scope. So we have to import this trait from the stir module. So over here we want to parse, and parsing again means converting a string into an integer. So we would here have an i32 type of this value, and over here the same thing. Now we can either annotate the type over here, or we could use the turbofish syntax, meaning we can directly annotate the type on the method, like that. And then, because the from string trait is actually implemented for the i32 type, we can also call the associated function from stir. Let's do 20 here. So this will convert from this string literal into an i32, meaning this will then hold an i32. Now, because all of them hold i32 integers, we can then do a mathematical operation, meaning we just add together all of these values, 5, 10, and 20. So the variable will hold an i32, and it should be equal to 35. And this is compiling. See you in the next topic. Now we will cover error handling, and the simplest form of error handling is to use the panic macro. Panic will print out an error message, unwind the stack, and finally exit the program. Now, unwinding the stack means that when you actually execute the program, then we have seen that the local variables and the function calls will be pushed to the stack. Now, when panicking, that means that the compiler will actually delete everything step by step from the stack memory and then exit the program. And in multi-threaded programs, it will exit the thread in which the panic occurs, not the whole program. So we don't deal here with multi-threaded programs. This will be another course, but I just want to mention it. So let's see exercises. As you can see, we have here a function drink, which takes a string literal. If the string literal is lemonade, then we print out success. Otherwise, we actually want to panic, right? Because we want to ensure that this line never gets reached, meaning never gets printed out. So when we pass over here lemonade, then this will print out success and then will panic. And this would be the output if a program panics. Thread main panicked at explicit panic, and it will provide you the line number at which the panic occurred. In this case, an explicit panic, because we have here called the panic macro. Common panic cases. Make the code work by fixing all panics. So when we call here the asBytes method on a string, then it will give us back the array holding the UTF-8 bytes of this string. Now we have seen that actually the UTF-8 representation of A would be 97, B would be 98, and C would be 99. So again, if assert EQ doesn't match, if this does evaluate to another value than this, then assert EQ will cause a panic. Over here we have a vector, and we try here to access the third index. Now we only can go to index 2, right? It's the outmost index we can provide. So let's change that. And this will then hold an I32, right? Because we are accessing a specific element. Unwrap may panic when get return a none. So the get method over here will return an option, meaning it either returns a sum with a value or a none. Now in this case, this would return a none because we don't have any value at index 3. So when we try to unwrap a non value, then we will panic. Now let's here access index 1, for example. Then it will return a sum 2, right? The first element, right? The element at index 1. And unwrap will basically just unwrap the inner value. So LA will then hold a value of 2 of type I32. Sometimes the compiler is unable to find the overflow errors for you in compile time, so a panic will occur. So when we call here the production rate per hour function with a value of 2, then let's see. We have here speed, the provided argument of type U8. And here we have CPH of type U8. Now, as you can see, we are inside here multiplying the speed, in this case 2, by CPH 222. Now this would actually result in an overflow because 2 times 221 would be 442, right? Now remember, an U8 can only represent up to the number 255. So this would actually cause a panic. But what we can do is just actually taking here a U16 and converting that to U16, meaning when we multiply these together, then the result of U16 will still be able to represent the resultant number. And over here we can do the same thing. And then let's see, because of the same reason as above, we have to wrap it in a function to make the panic occur. So here we are calling the divide function with two arguments, 15 and 0. So the divide function takes two arguments of type U8 and just divides it. Now this would also panic because we can't divide by 0. This is a mathematical rule and this will always lead to a panic. So let's here divide by 1, for example. Let's see if this is compiling. Alright, and again, when we use the get method, we will get back a reference to the value and not the actual value. So let's change that. And this is compiling. Detailed call stack. By default, the stack unwinding will only give something like this. So this would be the output if your program panicked. Though there is the reason of panic and the line of code is showing where the panic has occurred, sometimes you want to get more info about the call stack. Fill in the blank to display the whole call stack. Tips: you can find the clue in the default panic info. So when we run cargo run, this is basically how you execute a program you have written, and we'll cover that. Then you just provide over here this Rust backtrace equals 1 environment variable, and it will then give you detailed information about the panic that occurred. So over here, unwinding and abort. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. But this walk back and cleanup is a lot of work. The alternative is to immediately abort the program without cleaning up. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting by adding below content to cargo.toml. So we can here define in this cargo.toml file, and I will show you an example of that, how panic actually behaves. So we have two options here, either unwinding or aborting. When choosing abort here, then the stack won't get unwinded, meaning this will then be the responsibility of the operating system and not of the Rust compiler. Alright, see you in the next episode. So we have seen the option type, and the option type stands for a value that could potentially be absent. So let's now look at the result type. Result is an enum type that represents the outcome of an operation that could potentially fail. It has two possible variants: OK, a value t was found, and error, an error was found with a value e. And as you can see, the variants hold the specific information. The expected outcome is OK, the unexpected outcome is error. Since result is an enum, the possible variants can be matched using a match pattern, and that is what we call error handling. So let's see an example. Let's again consider the divide function we have seen before. So again, we can't divide by 0, meaning if the second argument here is a 0, then we should return an error, otherwise the program will panic. Now we can do here error handling, meaning we check if y is 0, right? Or in this case 0.0, because the arguments are floating point numbers. Now in case y holds a value of 0, then we return the error variant of the result enum, and we provided an error message. All right. So in this case, we use an explicit return keyword, meaning when this returns, it won't execute any further. It will directly return the error type and stop execution. Now in case y is not 0, then we will just divide x by y and wrap it inside OK, because remember, result is an enum, meaning we have to wrap the resultant value inside the variant. So that means when this function succeeds, then we will get back an F32, right? The result of this operation. And this is wrapped inside OK, because as you can see, we are returning a result type. Now in case of an error, we would return this string over here, wrapped in the error variant. And this allows us then, when we call the function divide with 2 arguments, that we can then match the result we get back here. As you can see, we would get back a result type, meaning the result type has 2 variants, either OK or error. And we can here use pattern matching to destructure the inner value, for example, this F32, into the variable val, which we then can print out. And in case of an error, we will get back this string over here, the error message. And we destructure it into this variable here and then print it out. Unwrap. The unwrap method takes as input a value of type result and takes out the value which is wrapped inside OK in case of success, or panics in case of an error. In case it returns an OK variant, we just take the value that is wrapped inside. Otherwise, the program will panic. So you should use unwrap only if you're 100% sure that the return variant will be OK. Otherwise, you should use match. And let's see the question mark operator. The question mark operator is a shorthand way to propagate errors or unwrap OK results. Basically, it's the same as unwrap, but instead of panic, it returns an error. It replaces an entire match statement and it can even be used in the main function. So as you can see over here in the main function, we can define here that main should return a result type. And as you can see, we have here a string holding a number. Then we try to parse this string over here into an I32 type. Now we have seen that the parse method could potentially fail, right? If we have here a string holding T, for example, the compiler can't convert it to an I32 because it's not a valid number. So in case we get back the OK variant, remember, parse will return a result. If we get back OK, then we just take the inner value and return it, meaning the inner value will then be assigned to the number variable. In case of an error, we want to return, meaning this over here won't get executed, it will return before. And we just provide the error message over here. And in this case, because we are using a function from the standard library, this error message is actually provided, right? So we just take the provided error message and return it. And if this didn't fail, it means this will get executed, and we just print out the unwrapped number. Now, because we return here a result type, we have to also return an OK in case everything succeeded. Now, because at the end of main, basically the end of the program has been reached, so it doesn't make sense to return any meaningful value. So we just return a unit type like that. So I've told you that the question mark operator actually replaces an entire match statement, meaning this over here would be exactly the same. So let's see. Again, we are in main and we return a result. Now, as you can see, we have again a string holding a number. Then we try to parse over here, and again, parse returns a result. So we have to handle the error case. Now we can do that appending to it the question mark operator, meaning in case this succeeds and it returns an OK with the value, in this case 10, but parsed as an integer, then it will just assign it to this variable, meaning number will then hold 10 as an i32. In case this fails, then it will return a parseInt error as defined in the parse method. Okay, so this over here is exactly the same like we did over here. And when this returns an error, the following lines won't be executed. In case this succeeds, then we have number which holds 10 of type i32. Then we'll just print out the parsed number, and then we return a unit type, because remember, we are here returning a result, meaning we have to also return OK variant in case of success. But again, because we are in main and this would be the end of the program, we don't return any meaningful value, we return a unit type. And there is also a concept called type alias. So it's basically just a way giving a name to an existing type. So if you like to write use64 like this, then you can create a type alias, meaning we can use the type keyword and provide a new name for a specific type. And as you can see over here, we are then using the new type we have created here. And this would at compile time then be replaced with the real type. And please don't confuse that with associated types in traits. They are different, okay? Let's see. Result is an enum to describe possible errors. It has two variants, OK and error. In short words, the expected outcome is OK, while the unexpected outcome is error. So let's see, fill in the blanks and fix the errors. First of all, we are importing the parseInt error from the num module, because we are using here the parse method, meaning it will, in case of an error, return the parseInt error. Now we have here the function multiply that takes two arguments of type string literals. Okay. Now, as you can see, we are here returning OK, meaning the return type will be of type result. And in case of success, or let's actually wait with annotating that. Let's first see what's happening here. So we are taking this string literal and try to parse it to an i32, right? So again, this parse method over here will return a result. In case of success, we would have OK and the value that was parsed. So for example, when we call here multiply with an argument of 10 for the first parameter, then we would have a parsed number 10, right? So we would have, in case of success, an i32 here. In case of an error, we would have the parseInt error, like that. And parseInt error is the error type that is defined for this method. Again, this is implemented in the standard library, so this has to comply with what is defined there. And N2 is exactly the same, but for the second argument. Then over here, we unwrap. And remember, unwrap will take a result and just unwraps the inner value. So in case we have OK, let's take the first argument 10. Then unwrap will just unwrap the inner value, meaning it returns the integer i32, right? That is wrapped inside the result enum. And then over here, we are multiplying by N2. Again, we have to unwrap because this is a result type. And if this succeeds actually, then we will return an OK, meaning OK will then hold in this case 10 times 2 will be 20, right? Like that. So we return an I32 in case of success. In case of error, we will return a parse int error, because that is the error that is defined from the parse method. So let's see, when we call multiply with these two string literals 10 and 2, then this should actually work, right? Because the compiler is able to parse these into integers. So it will parse here, and this will then be OK 10, and over here we would have OK 2. Then we unwrap both of these over here, meaning we unwrap the value from the variant, and here 2, meaning we multiply 10 by 2. And then this would be 20, and we wrap it inside OK, because we have to return a variant of the result enum, which means that the return type over here would be this, right? So result in case of success will hold OK and 20, right? Now in this case, this would actually fail because the compiler can't convert t to an integer. Now we want this to actually assert to 8, so let's do here 4. And this means this will get parsed to 4, and this will get parsed to 2, right? And then again, we just multiply these together and return it wrapped inside the OK variant. Meaning over here, we get back a result, and result will then hold OK and 8. Right? Now, if we unwrap the result over here, then it would unwrap the inner value, as you can see. So unwrap method allows us to unwrap the inner value. So OK 8 would be unwrapped to 8. Question mark operator is almost exactly equivalent to unwrap, but question mark operator returns instead of panic on error. So let's see, we have again the parseInt error. Implement multiply with question mark. Don't use unwrap here. So let's see. Again, we are taking two arguments of type string literal, right? 3 and 4 in this case. And let's start to implement. So we declare here n1, and we take n1 string and try to parse it into an I32, right? Now again, we should here use the question mark operator. So we append it after the method call here, and then we can only use the question mark operator when the return type of the function is a result, right? Because the question mark operator, in case of an error, will return the error variant and inside it the error value. So we return here a result. In case of success, it should be I32. And in case of failure, it should be this parseInt error, because again, this is defined as the error return value of the parse method. Now for n2, we do exactly the same. And that means if any of these fail, then it will immediately return meaning the rest of the function won't get executed and a parse int error will be returned. Now the question mark operator, in case of success, it won't return a result, it will unwrap. So for example, when we pass here 3 and this will get parsed, it will return OK and 3, right? And then the question mark operator, like unwrap, will unwrap the inner value. So n1 will then hold 3, meaning an i32 integer, and n2 the same thing. And then all we want to do is just returning an OK in case of success, because the return type is result. And we want to multiply n1 by n2. Notice over here that I didn't have to unwrap, because we have here i32 types, right? While over here we had to unwrap because these held result types. You have to remember that. Let's see. And of course I have to change that over here. Typo. And this is compiling. So what we had over here when we provide 4 as a string, we would have OK4, right? And then the question mark operator unwraps the value. And then over here we are multiplying 3 by 4, which would be 12. And then we wrap it inside OK to comply with the function signature. So this will then be the returned value, right? And then over here, as you can see, we are calling the function and unwrap it because we have here a result type. So we unwrap the inner value because this would return OK12, and we unwrap it, meaning the inner value gets unwrapped. Let's see over here, we have the file type from the FS module, and over here we are importing some stuff from the IO module. So over here we are opening a file, providing here to the open associated function the name of the file in form of a string literal, meaning this will then return a result, and in case of success it will hold a file, right? And in case of error it would be IO error. All right. And then we are matching F. Now F holds a result, meaning we must over here handle both cases in case of success and in case of failure. So if it is OK, then we unwrap the inner value, meaning the file, and we just assign it to F. In case of an error, we return the error wrapped inside the error variant of the result type, right? Because this function over here returns a result. All right. And then over here we are creating a new empty string. We then take F over here and read to string, meaning the contents of this file over here will be copied to this string, meaning S will then hold basically the contents of the file we have opened. And we have to provide here a mutable reference because this is defined in the standard library. And then again, because this read to string method returns a result, we have to match it. So in case of OK, then we will return over here a string, right? This string S over here. In case of error, we will return the error. And both of them, file open and read to string, return an IO error. All right. Now over here, fill in the blanks with one code line. Don't change any code lines. As you can see, we have here the function read file to, which returns a result. In case of success, it's a string. In case of error, it will be the IO error from this standard library. We here declare a new string, and we here initialize a new empty string. And I told you that the question mark operator replaces a whole match statement. So we can write all of this in one single line. So first of all, we are opening the file. So let's take this. And as we've seen, open will return a result. So we can use the question mark operator here to replace this whole match statement. So in case of error, it will immediately return, and it returns this error type. In case of success, then we will get OK and a string, and this will then unwrap it to the string, right? And in case of success, we will have a value of type file, like we saw over here. And again, file is a type defined in FS module. So we have seen that the question mark operator will then unwrap. We will basically get something like that, and it will unwrap the file inside the OK variant. What we then can do is call the read to string method on it, right? So we are calling read to string, and then again we have to append this question mark operator, because read to string also returns a result type, right? So in case of success, we will then over here mutate s, meaning the contents of this file will get read to this string, all right, or written to this string. And then we just return s, right, this string. And that means in case of success, we will have as return type a result that is holding a string. In case this or this fails, then it will return an IO error. Meaning if this fails, then over here a IO error gets returned, and this will never be executed. And if this fails, again, we return this error, and this will never get executed. Let's see. This is compiling. Map and then. Map and then are two common combinators for result TE, also for option T. So we have over here the parse int error, fill in the blank in two ways, map and then. So we have here the function add2, taking a string literal and returning a result. In case of success, holding an i32. In case of error, parse int error. All right, because this is the default error type of the parse method. Then we are taking this string literal and try to parse it to an i32. And then, as you can see, when we provide here add2 with a string holding 4, then we want to get back 6. So as you can see, when we provide 4, we will get back 6 over here. And that means we want to parse this string and then add 2 to the parsed number. And for that, we can use map, which is really convenient, because we not only want to handle this result case, but also then modify the value, right? So n here takes a closure, and we will cover closures very soon. So we provide here an argument n, and n would then hold the parsed number. And all we do is adding 2 to n, right? And that's all. So let's actually see the map method in the documentation. As you can see, maps a result TE to result UE by applying a function to a contained OK value, leaving an error value untouched. So when we call the map over here, it will it will apply a function if this method returns an OK value. If it returns an error, then it will leave it untouched. All right. So in this case, this would actually succeed, right? So parse over here will parse this 4 into an I32 integer, meaning it will then take the OK value and unwrap it. So n will then hold a 4, and then we just add n, and then we just add 2 to 4, right? Let's see. And this compiles. Now the second approach would be using and then. Now and then is very, very similar to map. The difference is here in the closure that the and then method takes. So let's go back to map here. So over here you can see this is the argument for the closure, right? And the closure over here returns directly the value, all right? And over here the closure itself will return a result. Now both of these methods return results over here, but the difference is in the closure, and you will see what I mean when we are looking at this. So this is very similar. It will take this parsed integer and then put the unwrapped value into n, and then over here we add 2 to n. Now we have seen that map would work like that, and then method will actually return in the closure itself a result. So we have to wrap that into OK like that, but otherwise they are exactly the same, and this succeeds. Number 5, with the return type rewritten, we can use pattern matching without unwrap, but it's so verbose. So here again we have the multiply function taking 2 string literals. In case of success, it returns an I32, otherwise parse int error. So over here we are using the match keyword. Now we want to parse the first string literal, the first argument. In case of OK, then we destructure it into the variable n1. So n1 will then hold the parsed number. In case of an error, we just return the error type. Then we match inside this match arm over here again. So we match the second argument, parsing it, and if this is okay, then we get out n2, all right? And then we can multiply n1 by n2 and return the result wrapped in the OK variant. Because as you can see, the function returns a result type. And in case of an error, it just returns an error. So this would be very verbose. So rewriting multiply to make it succinct. You should use both and then and map here. So let's see. we take first of all the n1 stir over here, the first string literal. All right. Then we want to parse it to an i32 integer, right? And let's then use and then. So if this succeeds, then we will have here n, which holds the parsed integer, right? And let's actually write it more beautiful like that. So we take then n, or let's call it n1, just to make a distinction. And then over here we want to parse the second one. Right, we want here the second one. And then if this also succeeds, we want to multiply n1 and the parsed n2 together. So let's use map here. And we would here have n2, right? Because map over here is called upon the parse method. So we would then get back n2. And then we just return n1 times n2. And notice, because we are using map here, we don't have to wrap it inside OK, right? So this will then return, for example, when we call it by 10 and 2, it will return 20. All right. And then we have seen that it will return the result type. So in case of success, it will return OK with an i32 value inside. Otherwise, it will return a parse int error. Let's see. And this is compiling. So as you can see, when we are calling the multiply function with 10 and 2 as string literals, it will parse the first argument, meaning we then have over here OK 10, right? And then over here we call the and then method. All right, so we take this n1 value here, basically unwrapping it, and inside and then we parse the second number. So in this case 2, right? So this will then get parsed into an i32, and we then can map, meaning we have n2 over here, and 2 in this case would be OK 2, right? And map will take and unwrap the value inside OK, meaning we then have n2, which holds 2 over here, and then we multiply n1 by n2 and return it. All right. And all we then do is here the returned value would be of this type, right? And in this case, this would return OK 20, right? Because it could parse these two numbers and it multiplied it and returned it. So we get OK 20. Then we pass that to the print function. As you can see, it takes as an argument a result type. Then we match it. If it is OK, then we print out the value wrapped inside OK, in this case 20. Otherwise, we will print out the error. And when we call multiply with an argument that can't be parsed, then we would get a parse int error, right? So this would then hold a parse int error. We are providing that to the print function, and then we match the argument, this tt, and this will then match the error, meaning the error will get printed. So in the first print call, n is 20, so we have successfully parsed these two numbers and unwrapped the value printing it. And in the second one, because we provide here an argument that can't be parsed, we get an parse int error. And this would be the error message that is provided in this standard library. So type alias, using this type over here everywhere is verbose and tedious. We can use alias for this purpose. So at the module level, creating aliases can be particularly helpful. Errors found in a specific module often has the same error type. So a single alias can succinctly define all associated results. This is so useful, even the standard library even supplies one IO result. So as you can see, we have here again the parse int error, and we want here to create a type alias. Now we have here the same multiply function we have seen above, so I won't cover that anymore, but the return type is defined as res i32. And the print function over here takes as an argument a type of res i32. Now, as you can see, exactly the same functions as we had over here, but we don't write out the whole type. We use here a type alias, so we can define that here. We use res i32, and we want to define that as a result. In case of success, holding an i32. In case of an error, as you can see, the parse method would return a parse int error. And then instead of writing that all the time in our functions, we can use this simple type alias. And of course, at compile time, these type aliases will then get replaced with this concrete type here. Let's see. And as you can see, the same output as before. Using result in fn main, typically the main function will look like this. However, main is also able to have a return type of result. If an error occurs within the main function, it will return an error code and print a debug representation of the error, debug trait. The following example shows such a scenario. So as you can see, we have here again the parse int error, and we define here in the main function that the return type should be of type result. In success, returning a unit type. In case of error, it will return a parse int error. So over here we have a string literal, and we are then trying to parse this string literal to an i32. Now again, parse returns a result, so we have to handle both cases. In case of OK, we just take the wrapped value and assign it to a number, right? In this case, this would hold an i32. In case of an error, it will just return the error, and it will stop execution from this point. And then all we do is we will print out the number. So let's see if this is compiling. As you can see, this is compiling. We are printing out the number. And don't forget, because we return a result type here, we have to return the result variant OK with a unit type in case of success. We provide here a unit type to the OK variant because the end of main means the end of the program. Because the end of main means the end of the program. So we don't have to actually return anything here, right? Because if the program ends, this returned value won't be beneficial. But we can just provide the unit type so we comply with the function signature. And by the way, as we've seen, we can here just use the question mark operator. So we can replace this match statement by this. And this is actually the reason most people use here in main the result type, because then it allows us that we use the question mark operator. Otherwise, if we didn't have result here, we can't use this operator. Let's see. Of course, I have to remove the match keyword here. And as you can see, this would be the same thing. All right, see you in the next topic. Let's take a look at Cargo. Now, Cargo is the official package manager and building tool in Rust. It helps automate tasks such as creating new projects, building, running, testing code, and managing dependencies. A crate is a compilation unit of Rust source code. So basically a crate is the smallest amount of code the Rust compilers considers at a time. And crates.io is the repository for Rust packages. So as you can see, this is the website of crates.io, and here you find some libraries. For example, we have here the rand library, and this allows for creating random numbers. And as you can see, you can add this very quickly into your own project, and we'll see how this will work. What is a crate? A crate can be of two types. Either it's a binary crate, and that means the program is compiled into an executable binary. It's basically a program you can run. And binary crates always have the main function in it. And a library crate. A library crate is compiled into a library, and it doesn't contain a main function, but it's considered a collection of reusable code that can be shared across multiple projects. And the crate root is the source file that is the root module of the crate. In binaries, it would be source main.rs, and in libraries, it would be the file lib.rs. Then we have modules. And a module is a way of organizing code by grouping together related items. Modules can be imported using namespaces, avoiding naming collisions. It also controls the privacy of its items like functions, structs, enums, and so on. When compiling, the compiler starts from the crate root. We have seen in a binary crate this would be in main.rs. And in a library it would be lib.rs. Then it checks if the modules are declared and looks for submodules. Submodules could be directly written in line with curly braces. It could be written in a separate file which has the module name ending in .rs. Or it could be in a separate directory which has the same name of the module and a mod.rs file inside it. And we'll do exercises and you will see how that works. So in case you want to follow these exercises, you actually have to install Rust on your system. So you can go to rustlang.org and then you can click install. And over here it will give you a command you can copy. Then running a terminal, and you can just copy this into your terminal. Now I'm on a Unix-like operating system, meaning I will use the Linux command, but the website will recognize your operating system and provide the appropriate command. So if you're on Windows, it will give you a command that you can paste into PowerShell, for example. So proceed with installation default. You can then press 1 and enter. Now I have already downloaded that, so I won't run it again. And then to check if everything is installed correctly, you can use these commands. First of all, we check, is the Rust compiler installed? If you get back a version, it means everything is installed. Then we check for cargo. This is fine. And rustup. And rustup is used for updating the version of Rust on your local system. Alright, so let's now see the exercises. A package is a project which you create with cargo in most cases, so it contains a cargo.toml file in it. So create a package with below layout. Now I will do that directly in the home directory, but you can do it at any location you want. So to create a new package, we can use cargo new and then provide the name of the package. So we want the name here to be hello package. And as you can see, the package has been created. So let's see cd hello package, and we are now inside our created package, right? So we have here cargo toml and a source directory. Let's see source. And if I print out the contents in main, as you can see, it contains a simple program that prints out hello world. So let me actually do it like that. So over here, if I now do a tree command, as you can see, we have exactly the same file structure here. We have a cargo toml and then a source directory with main.rs inside. Let's print out the cargo toml. And as you can see, this matches the file in the exercise. Create a package with below layout. So over here, we want to create a library. So I'm back in my home directory and we can create the library crate right now. Let's do cargo new, then the package name here. And then we have to provide the lib flag, right? So this will then create a library. And then let's cd into that. And as you can see, we have cargo toml and a source directory. Now, let me print out the cargo toml file. And as you can see, again, this matches. And if we go to the source directory, as you can see over here, we have a lib.rs file. And this just has a basic add function over here together with some tests. All right. Fill in the blank with your answer. What's the difference between package number 1 and package number 2? Now the difference would be package number 1 is a binary crate. And package number 2 is a library crate. All right. Crate. A crate is a binary or library. The crate root is a source file that the Rust compiler starts from and makes up the root module of the crate. In package hello package there is a binary crate with the same name as the package, hello package, and source main.rs is the crate root of this binary crate. Similar to hello package 1 also has a crate in it. However, this package doesn't contain a binary crate but a library crate, and source lib.rs is the crate root. So what's the name of the library crate in package hello package 1? The answer would be hello package 1, right? Because as we've seen over here, in the package hello package there is a binary crate called hello package, and that means in a package hello package 1 the name of the library crate would be hello package 1. And by the way, a package is what we have seen over here. Basically, when we create a new project, right? When we create a new project, we create a new package. And a package consists of a cargo.toml file and a source directory together with other stuff. Add a library crate for hello package and describe its files tree below. Alright, so we want to add in the hello package a library crate. So let me remove this over here, and we will go inside hello package. Now over here in the source directory, we want to create a new library crate. As you can see, we have until now a binary crate. So let's create lib.rs. Touch is a Linux command that allows to create a new file. So then we would have librs and main.rs. So when we look at the tree, as you can see, we then have the cargo.toml, the source directory, and two crates, one library crate and one binary crate. So this would then hold lib.rs and main.rs. After this step, there should be two crates in package hello package, a binary crate and a library crate, both with the same name as the package. A package can contain at most one library crate, but it can contain as many binary crates as you would like by placing files in source bin directory. Each file will be a separate binary crate with the same name as the file. So create a package which contains three binary crates: hello package, main1, main2. One library crate. So what we want over here is to have in the source folder the lib.rs and main.rs. Then inside the source folder we want to have a bin directory which holds main1 and main2. Right? So as we've seen, we can have as many binary crates as we want in a package, but only one library crate. And over here we have some other directories. So we have tests for integrated tests, benches for benchmark, and examples. So let's create these over here. So as you can see, inside source we already have a library crate and a binary crate. Now we want to create a new directory called bin. Then we cd into bin and we create main1.rs and main2.rs. So again, when we go to the root of the package, as you can see, we have cargo toml, the source directory. We have inside the source directory a bin directory holding two binary crates, main1, main2, and we have in the source directory lib.rs and main.rs. Yep, as you can see, the above package structure is very standard and is widely used in many Rust projects. So let's see modules. Modules let us organize the code within a crate into groups for readability and ease of reuse. Module also controls the privacy of items, which is whether an item can be seen by outside code, public, or is just an internal implementation and not available for outside code, private. We have created a package named hello package in previous chapter, and it looks like this. Now we actually created over here a bin directory, so let's delete that. I go into source and then remove the bin directory. So as you can see, the tree looks exactly the same. Now it's time to create some modules in the library crate and use them in the binary crate. Let's start. So as you can see, we can define some code in the library crate and then use it in the binary crate. So implement module front of house based on the module tree below. So in the library crate, we want to create a module front of house, and this should then hold two submodules, hosting and serving. Now hosting holds two functions and serving holds 4 functions. So as you can see, we would do that in the library crate. All right. And again, modules allow us to structure our code. So let's open lib.rs and I will copy this over here. So we have to implement front of house. Now we have seen that front of house module should contain two submodules, namely hosting and serving. Like that. So we have a front of house module that contains two submodules, hosting and serving. Now we want to add these functions over here, add to waitlist and seat at table in the hosting module. Add to waitlist, add to waitlist and seat at table. So as you can see, front of house containing one submodule, hosting, holding two functions over here. Now let's see serving. I will just copy that. Like that, and doing it like that. As you can see, the serving module holds 3 functions. And when we run the code, actually, we can use the cargo run command. And as you can see, this is compiling, but it gives us warning that we didn't use these functions over here, which is okay. And of course, hello world will get printed from the binary crate, right? Because main just prints out hello world. Let's call add to waitlist from a function eat at restaurant, which is within the library crate root. So inside lib.rs, we are below the module front of house, we are creating a new function. Like that. Call add to waitlist with absolute path. So it's like in a file system, you can have absolute paths and you can have relative paths. So in this case, we want to use the absolute path to the add to waitlist function over here. So we would use for the absolute path the crate root. Then we want the front of house module, and we want the submodule hosting, right? And then over here, we can call the function like that, add to waitlist. Now this would be considered the absolute path. Now over here, we are using the relative path. So we are actually already in the crate root, right? So that means we don't need to use crate here. We can directly access front of house. Hosting. And then call the add to waitlist function. Now, as you can see, it gives me here an error. Module hosting is private. So we can make this public using the pub keyword. All right. Now the same thing with the functions. Let's make them public. Like that. You can use super to import items within the parent module. So again, in lib.rs, we want to create another module. So let's copy that. I will put it below the front of house. And as you can see over here, we have the back of house module with two functions declared inside it. So we have fix incorrect order, and inside this function, we call the cook order function over here. Fill in the blank in 3 ways, using keyword super, using absolute path. So in order to access the function over here, serve order, let's first use the super keyword. So super means we go 1 level up, right? So we are here inside the module back of house. So we go 1 level up, which would be the crate root, right? lib.rs. So we use super. And then we can access front of house. And I guess hosting, no, serving, and serve order. Like that. And again, serving is private. Let's do that. Let's make it a public function. And again, serving here is private. So let's make that public. And also the function here, like that. And the second way would be using absolute path. So again, we can use here crate, right? Crate would refer to lib.rs because it is the crate root of this package. separating modules into different files. So as you can see, we want to put these modules into their own distinct files. Please separate the modules and codes above into files resident in below dir tree. So as you can see, we have here main and librs crates, and here we have the modules we want to split up. So we have the module front of house, holding hosting and serving. These are submodules and mod.rs. And we have over here back of house.rs. Now we have said that there are three ways to declare modules, right? The first way would be in the crate root, for example, lib.rs. We define a module and put it right inside the curly braces, right? All the code is inside these curly braces, right? The second way would be to, in lib.rs, declaring the back of house module, but without curly braces, right? Only declaring like this, for example. Only declaring the module. And that means the compiler will then check, is there in source directory a file named as the same name as we gave it to the module, right? So we declared a module in lib.rs, and then we have to create a file ending in .rs with the same name as the module we have declared. And the third way would be, if we want the module to be a subdirectory of source, then we have to again declare front of house inside lib.rs, the same way we did before, but we create a directory instead of a file with the same name as the module. And then, very important, the code of the module will then be in mod.rs. Now in our case, we are declaring in mod.rs two submodules, hosting and serving. All right. So we want to have this code separated in different files, and this is how it should look like. So let's start with back of house. All right. I will copy that. And first of all, I will delete anything in here. And let's declare the module back of house, right? Now we have here declared a module. As you can see, the file is not found. So we can here declare back of house.rs, and then we can put the code of the back of house module directly into this back of house file. We're moving this over here because we have already declared the module. And as you can see, back of house file now contains only the code related to this module. Again, we have in lib.rs declared the back of house module. Then we have over here created a file that has the same name as the module, right? And in here we are providing the code like that. And because we have already declared the back of house module, we don't have to redeclare it inside here, right? Now, as you can see, we also want front of house. Now the difference is front of house should be a directory holding two submodules. So let's first of all, in lib, we want to declare front of house module, like that. Then we create the directory with the same name as the module. Like that. Then the first thing is we create a file mod.rs. This is now the create root of this. This will be considered the root of this module, mod.rs. And as you can see, we want here inside front of house two submodules, hosting and serving. Let's declare them. Like that. And then we can create both of these files. Let's start with hosting. And we just take all the code from the hosting module here. Like that. And let's create serving. And we just take the code here from the serving module. Like that. Let me remove the comment. So, and now if we go back to the source directory, as you can see, we have back of house. This is a module. We have front of house, hosting and serving. These are two submodules. And we have here mod.rs, exactly like we wanted here. Now over here, by the way, this function eat at restaurant will be directly in the lib.rs. So as you can see, instead of defining the module and putting all the code in curly braces, meaning inline, we can use different files to restructure and reorganize our code. And this makes the lib.rs file much more clean and readable. Accessing code in library crate from binary crate. Please ensure you have completed the fourth exercise before making further progress. You should have below structures and the corresponding codes in them when reaching here. So we have done that. Now we will call a few library functions. Now we will call a few library functions from the binary crate. So let's copy that into the binary crate. Like that. Now we want to call a function. So the output should be sit down please, and then a second function which returns yummy yummy. Now, as you can see over here, we have to call the eat at restaurant function to get back yummy yummy, and sit down please would be in the front of house module, in hosting, and seat at table function. So let's see. First of all, I want here the module front of house. Alright, because the binary crate and the library crate are separate from each other. So the binary crate over here can't know what is defined in the library crate. And then over here, we can, as the crate module, and then here we can use an absolute path providing the crate root. Now we have to actually provide here the name of the crate, meaning hello package. All right. And then we can call front of house. And let's see, front of house hosting seat at table. Seat at table, like that. And then over here we call hello package and then eat at restaurant. This is defined in our lib.rs. So again, instead of writing here crate, we write the name of the package because we are here in the binary crate. So we can use the crate keyword in lib.rs, but in main.rs we have to provide the name of the package. Let's run that. And as you can see, we have some errors. Module serving is private and module hosting is private. So to actually access that from the binary crate, we have to make them public. So let's see. First of all, we go to lib.rs and we want these two modules to be public. So let's make them pub like this, which means that these two modules are now accessible for our binary crates, the main.rs file. Then let's go to front of house. And let's here make these two modules or these two submodules also public. Like that. And if the module itself is public, that doesn't mean that the inner functions, for example, or structs or anything that is inside the module is also public. So we have to declare here, as you can see, this is already done, that these functions are also public if we want to access it. And as you can see, serving also has the public functions. Now let's check again in lib.rs because we are calling here a function. All right, this is also public. Let's run it again. And as you can see, this is actually compiling. It just over here complains that we didn't use some of the functions, which is okay at the moment. Now, instead of just asserting, let's actually print that out. Yeah, let's do it like that. As you can see, the output will be sit down, please. Let's call the second one. So we want to get this. Like that. Let's see. I copied here the whole assert. We don't need this actually. Let's see. And as you can see, the output will be sit down please and yummy yummy. So we have successfully restructured and reorganized our whole code into different files and folders, meaning it is much more organized and much more readable. Alright, see you in the next topic. We will now take a look at the debug and display traits. So types which want to be printable must implement either debug or the display traits. And automatic implementations are only provided for types in the standard library. So this doesn't apply to our customly created types. A debug trait can be implemented by simply using the arrivable trait. And a display trait must be manually implemented. Let's see. We have here println and format. Printing is handled by a series of macros defined in standard format, some of which include format, write formatted text to string, print, same as format, but the text is printed to the console. Println is the same as print, but a new line is appended. ePrint is the same as format, but the text is printed to the standard error. And ePrintln, same as ePrint, but a new line is appended. All parse text in the same fashion. All parse text in the same fashion as a plus Rust checks format correctness at compile time. So let's see, we have here a string literal and we use here the format macro, meaning the return type will be string. And we want here s to hold a string of hello world. So again, we use the format macro like we would use the println macro we have been using. So in this case, we want to take s1 over here and then just append the rest. So we take hello, this will be placed here, and then the rest. And this is compiling. Let's actually print that out. As you can see, this would be the output when printing out s. Print println, fill in the blanks to make it print hello world, I am, and then on the new line sun face. So over here we want to use print, because as you can see, I am should be on the same line. So as we've seen, print macro doesn't append a new line character. Now a new line is defined in C like that, all right? And this is a symbol that the compiler knows that it should treat it as a new line. But in this case, print doesn't append it, so the next line will be on the same line as this print statement. So let's use here println, because as you can see, after I am, we want to have a new line. And then over here, we can again use println. And this would be the output. Debug and display. So all types which want to be printable must implement the standard format formatting trait, debug or display. Automatic implementations are only provided for types such as in the standard library. All others have to be manually implemented. Let's first look at debug. The implementation of debug is very straightforward. All types can derive the debug implementation. This is not true for display, which must be manually implemented. And we have used that before. This is the debug notation, must be used to print out the type which has implemented the debug trait. So as you can see over here, we have a custom type. This structure cannot be printed either with display or debug. To make this struct printable with debug, we can derive the automatic implementations provided by Rust. So again, we can use a derivable trait, meaning this struct over here implements the debug trait, meaning we can print it out using debug notation. So fill in the blanks and fix the errors. As you can see, we have here a custom type structure holding an i32 value. Types in Standard and Rust have implemented the debug trait. So as you can see, this is of type i32. Now all of the types in the Standard library have implemented debug or even display. So we can use here the display notation, and this will print out fine. Now over here, we must use debug notation because this is a type that we have created. And again, to use the debug notation, we have to derive the debug trait. Like that. And that means structure implements the debug trait and we can then print it out. So this i32 type will be printed automatically because it's a type defined in the Standard library. And over here, we just had to derive the debug trait and then use debug notation here. So format debug definitely makes one type printable but sacrifices some elegance. Maybe we can get more elegant by replacing this notation with something else, but not this. Alright, let's see. We have here a custom type that derives the debug trait. Then we are here instantiating it. And when we now execute the program, as you can see, the output will be like this. Now we want the output to look something like that, and we can for that use the pretty notation, just adding this hashtag symbol between the colon and the question mark. And then the output should look much more pretty. As you can see, the output will then be like this. And notice we first had to derive the debug trait in order to print it out using debug notation. We can also manually implement debug trait for our types. So as you can see, we have here two custom types, structure and deep. Now structure holds a type of i32 and deep holds a type of structure, meaning these are basically nested. So we have deep, which holds a structure, which holds an i32, right? The problem with derive is there is no control over how the results look. What if I want this to just show a 7? So as you can see, we are here instantiating it with a value of 7. Now when we print it like that, then as you can see, the whole structure will get printed out, but we only want the value over here. So what we can do is we implement the debug trait manually, meaning we can manipulate the output. So let's see the debug trait in the documentation. And as you can see, this is the debug trait as defined in the Standard library. So let's copy this function signature. So we can then over here implement the debug trait and this is found in a module and this is inside the module FMT from the standard library, and we want to implement it for the deep over here. Now we remove that, and we also remove that because we are implementing debug trait manually, right? We don't need the derived implementation. So let's see, deep, then I will copy the function signature. So here we can use a custom type FMT result. And you know what? We can use a namespace here. So then we don't have to write here standard all the time. Like that. I can delete this lifetime. And now we can implement the debug trait, namely this FMT method. So again, we want to write to a buffer. So we use the write macro, and it should write to this formatter, which is provided by the debug trait. And then over here, all we want to actually print out is, in this case, self, right? The instance over here. And then we access the first element. So when we access the first element in a tuple, we use the dot notation like that. And inside here, we have now accessed structure, and we want to access this value, the structure struct holds, right? So we again use 0. And that's basically it. Now it should print out. And of course, over here, FMT formatter. This is also from the FMT module. And as you can see, now 7 will print. So all we did over here is manipulating how the output of the debug trait looks like when we use debug notation. And as you can see, we have defined for the deep custom type over here how the output should look like. So the output will just be the inner element of deep and structure, right? This I32. And we just access that and write it to this buffer. All right. Display. Yeah, debug is simple and easy to use, but sometimes we want to customize the output appearance of our type. This is where display really shines. Unlike debug, there is no way to derive the implementation of the display trait. We have to manually implement it. Another thing to note, the placeholder for display is this and not that. So this would be for debug trait. For display, we are using that, and you know that already. So make it work. As you can see, again, we are using the FMT module, and we have a custom type, point2D, holding two fields of type F64. Now we want to implement the display and the debug trait for this custom type. Meaning, when we instantiate this point2D, then we can pass the instance over here and it will give us this output, right? So we are using here the display notation and debug notation. And as you can see, we can here define different outputs. So when we pass an instance of point, then the display trait actually will output something like that. If we use debug notation, then we want the output to look something like that. And that's what I mean when I say we can manipulate how the output of a custom type will look like. So I will take over here this method and I will just copy it over here. Now let's first implement the display trait, as you can see, we want the output to look something like that. So we define here display the x field, the value of x field, and then plus the value of the y field, and we have here an I, okay, like that. And we can access these fields using normal notation self.x and self.y, right? And for debug notation, we want the output to look something like that. So let's copy this, put it inside here. And as you can see, we want here the value of the x field and here the value of the y field. And as you can see, we are here using curly braces, and this is usually for the placeholder. So what we have to do here is using two of them, meaning this curly braces over here will basically be escaped. All right. And then over here we have to provide the arguments self.x and self.y. Let's see. And this is compiling. Now let's see the actual output. As you can see, I'm using display notation and debug notation and just provided an instance of the point to the type. And as you can see, this will then be the output. So question mark operator implementing FMT display for a structure whose elements must be handled separately is tricky. The problem is each write generates a FMT result which must be handled in the same place. Fortunately, Rust provides the question mark operator to help us eliminate some unnecessary codes for dealing with FMT result. So, let's see. Again, we are using the FMT module and we have here a custom type, a struct list, a tuple struct list holding a vector of I32 elements, right? Over here we are instantiating this list with a vector holding 1, 2, 3. Now as you can see, when we put this list over here into the format macro, then we want the output to look something like that. So we want to print these square brackets, the index, colon, and then the actual value. Now let's see how this would be implemented. Notice over here we are implementing the display trait, so we can then use it to display the type directly. So as you can see, this is the function signature from the FMT module. And as you can see over here, we return a type of FMT result. Now this is a type. Now this would be a type alias, and we have covered that. Now over here, we want to extract the value using tuple indexing and creating a reference to vec. So the first thing we do is we want to access the vector in the list struct, and we do that using tuple indexing, right? We want the first element because there is actually only one element on here. So we access that, meaning we will get back a reference to a vector holding I32 types, right? Here we are taking a reference. Now, then we have basically unwrapped this vector into this variable. Now, as you can see, we use the write macro to write to this buffer this square bracket, because as you can see, this is what we want to output. So the first thing added to the buffer will be this square bracket. Then iterate over v in vec while enumerating the iteration count in count. So we take this vector and we iterate over it and enumerate, meaning we will get back a tuple holding the index and the actual value. Then for every element except the first, add a comma. Use the question mark operator to return on errors. So as you can see, if count is not equal to 0, meaning if it is in fact the first element, then we don't add this comma, all right? Because we don't want to look something like that. So this is only after the second iteration that this comma will be added. And then we write the actual value over here. And this iterates 3 times, right, for each element. And then in the end, it will put into the buffer this square bracket. So when we run that, as you can see, the output would be something like that. But this is the output that we want. So what's missing over here is we didn't include the indexes, right? So what we can do over here, we want here to be the index and then a colon like here and a space and then the value. So we have the index in this count variable. So let's use that. And again, we can then run the program and this succeeded. So let's actually print that out. As you can see, this would be the output. So we can really manipulate the output of our custom types using the debug and the display traits. And by the way, as you can see, we are here using the question mark operator because this over here could potentially fail, right? That's why we are using this here, and we use here the result type from the FMT module, just in case any of these operations here fail. All right, see you in the next topic. So let's take a look at lifetimes. Now lifetimes are only necessary when dealing with references, and even then, most of the time the compiler can actually infer the lifetimes and we don't have to worry about it. So let's see. A lifetime is another kind of generic, ensuring that references are valid as long as needed. Every reference has a lifetime, which is the scope for which the reference is valid. Most of the time this is implicit and inferred, so we don't have to worry about it. Sometimes though, lifetime annotations are needed, and that's the case if the compiler can't infer it. And lifetime annotations is a concept which most other programming languages don't have. So even for experienced programmers, this sometimes looks a little bit confusing, but in actuality, it's a very simple concept and you will understand it very quickly. So actually, the main aim of lifetimes is to prevent dangling references, also called dangling pointers. So let's see, we are here in main and we declare a variable r. We don't initialize it with a value, but just declaring it. Meaning the compiler will actually infer a lifetime of a for this variable. And the lifetime a in this case is valid until the end of the main scope, right? Then over here we have an inner scope. And in this scope, we are initializing variable x with a value of 5. So the compiler will annotate this variable to be of lifetime b. And as you can see, lifetime b is only valid until the end of this scope. Now then we are assigning a reference to x to the variable r, meaning the variable r we have declared here holds a reference to the variable x. The problem here is that when x goes out of scope at this point, then r points to something that is not valid anymore, right? And that's the aim of references, to avoid exactly this scenario. Now, to understand lifetimes, you have to understand the borrow checker in Rust. So the borrow checker compares scopes to determine whether all borrows are valid. It's a key part of Rust's ownership system. It tracks lifetimes of references and ensures that they don't violate the ownership rules. These rules ensure that a value is not accessed after it has been moved or freed from memory. And important, a reference to a value must never outlive the value itself. So you have to remember especially the last line. A reference to a value must never outlive the value itself. So when we go back here, as you can see, we have here a reference to value 5. Now the problem is that this reference outlives the value itself, meaning x holding this value we are referencing to goes out of scope, meaning the reference on here lives longer than the actual value it is referring to. Alright? Let's see. The compiler uses lifetime to ensure all borrows are valid. Typically, a variable's lifetime begins when it is created and ends when it is destroyed. So, the scope of lifetime. Annotate the lifetime of I and borrow2. Lifetimes are annotated below with lines denoting the creation and destruction of each variable. I has the longest lifetime because its scope entirely encloses both borrow1 and borrow2. The duration of borrow1 compared to borrow2 is irrelevant since they are disjoint. So when we look at this program here, what you see is that we have here initialized variable I, right? Now this variable I over here lives until the main scope ends. Alright? Basically, it outlives this scope and this scope. Now over here, we are assigning a reference to I to borrow1, right? So borrow1 lifetime starts. And then we are just printing out borrow1. Now over here, borrow1 will go out of scope. But it doesn't matter because the value itself still lives on. Alright? And over here the same thing. We have borrow2 which holds a reference to I. Meaning that borrow2 lives inside the scope. So we print here borrow2 and then it will here go out of scope. But again, the value here lives on. So the actual value outlives the borrows or the references. Alright? Example 2. So over here we have a variable x with a value of 5. And then over here we have a reference to x assigned to variable r. And then we are printing out r, right? So if we execute that, it will compile. Because again, as you can see, we are declaring here the variable x in this scope. So variable x will live until the scope ends. And the same thing for the reference to x. So the reference to x is assigned to R, meaning R will live until the end of this scope. So the value and the borrow to the value are both valid. All right. And over here you can see the lifetime annotations. The important thing here is that both the value itself and the reference to the value are valid, right? The reference here doesn't outlive the actual value it is pointing to. Annotate R and X as above and explain why this code fails to compile in the lifetime aspect. And that's actually the example we have seen. So we are here declaring R, and over here in this inner scope, we declare a variable x and initializing it with a value of 5. And then we are assigning a reference to x to R. The problem here is x will go out of scope, so R still points to this location, but this over here has gone out of scope, right? So Rust won't allow you to compile this program, and you will get a compiler error saying x does not live long enough, right? Because the reference to the value lives longer than the actual value lives, right? Meaning the lifetime of x is shorter than the lifetime of R, or the lifetime of x holding the value is shorter than the lifetime of R holding the reference to a value, and this should never happen. So lifetime annotating, the borrow checker uses explicit lifetime annotations to determine how long a reference should be valid. But for us users, in most cases, there is no need to annotate the lifetime, because there are several elision rules. Before learning these rules, we need to know how to annotate lifetime manually. So, ignoring elision rules, and that's the next topic, lifetimes in function signatures have a few constraints. Any reference must have an annotated lifetime. Any reference being returned must have the same lifetime as one of the inputs or be static. So over here we have a function print1, and it takes as an argument a reference to an i32 type. All right. Now this is how we would annotate a lifetime. It's actually very similar to generics, but we use this apostrophe syntax and a lowercase letter, by convention just going from A, B, C, D, and so on. So in this case, we annotate here that the reference here is of lifetime A. So when we have over here a lifetime annotation, then we can provide here, then we can annotate it here for our reference, right? And again, we are just dealing with lifetimes when we are dealing with references. So in this case, we say the reference to the i32 type should be of lifetime A. Now, when we annotate that to our function, it means that the lifetime A must at least live as long as the function itself. Or we could also say lifetime A must outlive this function. So the past reference over here must outlive this function. And this is just ensuring that the reference passed here lives longer than this function, meaning we can ensure that this function always deals with a valid reference, right? And all we do here is printing out x. Mutable references are possible with lifetimes as well. So if you would have a mutable reference, you would annotate it like that. First, after the ampersand, of course, you will always put the lifetime annotation, and then the mute keyword, and then of course the type. Multiple elements with different lifetimes. In this case, it would be fine for both to have the same lifetime A, but in more complex cases, different lifetimes may be required. So as you can see, we can define more than one lifetime. Over here we have lifetime A and lifetime B, meaning the references passed to this function could be of different lifetime. But again, lifetime A and lifetime B must outlive this function. So the past references over here must outlive the function, right? And returning references that have been passed in is acceptable. However, the correct lifetime must be returned. So let's take a look at the function passX. As you can see, it takes two arguments and both of them are references. Now this would be of lifetime A and this would be of lifetime B. Again, both of these references must outlive this function. And we are just returning X, which is annotated with a lifetime A. Meaning the return type will be a reference to an I32 with a lifetime of A, right? This would be the type that is annotated to the X argument here. If we would here have Y and we return Y, then we would do it like that, right? Because we are returning a reference with a lifetime annotation of B. So as you can see, we have here two variables holding I32 types. And then we are passing to all of the above functions the reference to these two variables, right? Because all of these functions over here expect a reference to an I32 type. Now, in this case, this program will compile. As you can see, this is compiling because we have here declared X and Y in the main scope, meaning they are valid until the end of the scope over here, right? So the X and Y references we pass to the functions outlive all the functions, which is a requirement, right? The past references must outlive the function, so we don't have to deal with dangling references. And so let's see an exercise to understand it even more. Make it work by adding proper lifetime annotation. So over here we have the function longest that takes two arguments of type string slice. Now we then test the length of these string slices, and if x is longer than y, then we return x. Otherwise, we return y. So if we go over here in the main function and let's do some variables. As you can see, we have two string literals, long and longer. Now, we would pass that to this function over here. Now, it could be possible, in this case, the return type is known at compile time, but sometimes this is decided at runtime. And when we are passing these arguments to the function over here, let's do that actually. And notice we don't have to pass here a reference because string literals are already references. All right. Now, if we would compile that, this would actually fail, right? Missing lifetime specifier. So what we want to achieve here is, first of all, we want to add a lifetime parameter like that. And then we want to define the lifetimes of these references. Now in this case, the function over here could either return x or y, right? Depending on which argument has the longer string, right? So sometimes it might be x that is returned and sometimes it might be y. So we can't be sure if we annotate here a and b like that. We don't know which one will get returned. Is it A or B? It depends on the arguments, right? So what we can define here is that X and Y, these two arguments, have the same lifetime, meaning these two references share the same lifetime. They must be declared in the same scope. And both of them, of course, must outlive the function longest. So in this case, this is what we are providing, right? We are declaring x and y over here in the main scope. So when we call the longest function with these two references over here, it means that these two references still live on even after this function call, all right? Because again, the reference of x and y will live until the main scope ends. Now, because we have here defined that both of these references have the same lifetime, it is clear that the returned string slice must have the same lifetime, either x or y, right? Let's see. And as you can see, this is compiling. In this case, longest will return y because it is longer than the x string. All right. A must live longer than the function. Here, reference to string foo would create a string followed by a reference. Then the data is dropped upon exiting the scope, leaving a reference to invalid data to be returned. Fix the error in 3 ways. As you can see, we have the function invalid output. We define here a lifetime parameter a and declare that the returned reference should be of this lifetime. Now, the problem here is we are creating a new string and returning a reference to it, right? We are returning a reference to a string. The problem is this string was declared inside the function. Now, when the function returns to the caller, it means the string over here will get out of scope, right? Because it is declared inside the function. So again, if we call, for example, if we call this function, then we would get back a reference to a string, right? The problem is that the reference points to something that isn't valid anymore. This string declared here got out of scope. So x points to something that is not valid anymore. So returning a reference to something declared inside a function is a really bad idea. Now what we can do over here to fix that, and this is probably the easiest fix, we just return the string itself, right? So then ownership will be transferred and x will be the owner. All right, let's print out x. As you can see, this is working because we are here declaring a string and then return it, meaning the ownership of the string will then be returned over here, right? So X will become the owner of the returned string from the invalid function. The second way to fix that would be returning a string literal, right? And a string literal actually has always a static lifetime. We will come back to that, but that actually means that this reference is of static lifetime, meaning it is valid throughout the entire program. All right? Because remember, a string literal is hard-coded into the binary, so it lives as long as the program lives. So then over here we will get back a string slice, right? Let's see. And as you can see, this is also compiling. The third way would be, we over here create a string. And then we can pass this string to the invalid output. So in this case, we want here to take a reference to a string, right? We can also write it like that, because remember, a reference to a string will be automatically inferred to a string slice, right? So we are then passing a reference to this string, right? And what we want to return here is S, meaning we return here a string slice. And we can annotate a lifetime parameter and then we will print out X. Let's see. And this is also working, because as you can see, we have defined here a string, meaning S over here is the owner of the string. Then we are passing a reference of S to this function, right? We annotate here a lifetime A, meaning the reference over here passed to the argument S must outlive this function, which it does, right? We have declared S here, so even after this function call, S still lives on, right? And then all we do is we again return S, the passed reference, right? So it will actually have the same lifetime as the passed argument, right? Meaning we have here then a returned string slice. All right. Printfs takes two references to i32 which have different lifetimes A and B. These two lifetimes must live at least as long as the function printfs. So as you can see, we are here in the printfs function declaring two lifetime parameters, one for argument X and one for argument Y. Again, we are dealing with references, meaning we care about the lifetimes. If these would be owned types, like so, then we don't deal with references, right? And then we just print out X and Y, the provided arguments. Make it work, a function which takes no arguments but has a lifetime parameter A. So over here, we can see that we annotate a lifetime parameter A, and we have here an i32 integer. Now error, X does not live long enough. So we assign to Y over here a reference to X. The problem again is that when we annotate this lifetime parameter, it says the lifetime A must outlive this function, which it doesn't, right? Because the reference over here, because the value we are referencing to is declared inside the function, meaning it will then be dropped at the end of the scope. Attempting to use the lifetime A as an explicit type annotation inside the function will fail because the lifetime of reference X is shorter than A. A short lifetime cannot be coerced into a longer one. So let's see, in main, we are here destructuring a tuple into the variables 4 and 9, right? So 4 will hold 4 and 9 will hold 9. Borrows of both variables are passed into the function. So we are then calling the print_refs function with references to 4 and 9, right? This function over here. Any input which is borrowed must outlive the borrower. In other words, the lifetime of 4 and 9 must be longer than that of print_refs. So again, when we annotate these lifetimes on a function, both of the lifetimes must outlive the function, or both of the references passed here must outlive the lifetime of this function, which they do, right? So 4 and 9 are declared in main scope, meaning they outlive this function over here. So this should actually work. So failed borrow contains no references to force A to be longer than the lifetime of the function, but A is longer, because the lifetime is never